Hi, I'm Rob Furnett, and this is a video demonstration of my final project for CSCI E-89 Deep Learning at Harvard Extension School in the fall 2025 semester. My project is a local AI assistant which leverages large language models and retrieval augmented generation techniques to provide contextual assistance and information retrieval on AI Agent Ensure, a fictitious company created for this project. The implementation runs locally on Ollama on my Mac Studio with an Apple M1 Max chip, 10-core CPU, 32-core GPU, and 64 GB of RAM. It uses open source models and frameworks, with the core technologies being the Llama 3.2 LLM with 3 billion parameters for inference, nomic-embed-text for embeddings, and sentence transformers for embedding support. PyPDF is used for PDF document loading, and LangChain for the RAG pipeline, conversational chains, and memory management. ChromaDB provides vector storage and semantic search and document retrieval, and SQLite is used for structured data such as insureds, policies, and claims. The web interface is implemented in Gradio, and OpenAI Whisper is used for speech-to-text translation, and Mac OS Say and FFmpeg for text-to-speech translation. Now, for the demo, I'll go ahead and launch local Ollama server, then run a script to create the SQLite database from CSV files and load PDF files into the Chroma vector store. Then I'll launch the AI agent so we can walk through the demo. First, I'll enter a text query, then submit the query to the agent, which will use intelligent routing to determine if the data should be retrieved from the RAG vector store or from the SQLite database. Which, in this case, RAG was used to pull data from the Chroma vector store from the overview and Agentic AI liability insurance document sources. On the right, we see both the text response as well as the audio response, which we can listen to.
AI Agent Ensure is a next-generation insurance provider dedicated to safeguarding companies developing and deploying agentic AI systems, autonomous robotics, advanced RAG pipelines, and AI-native workflows.
For the next query, I'll send audio input to the agent. What products does this company offer?
What products does this company offer?
And again, we have both text and audio responses.
AI Agent Ensure offers a comprehensive portfolio of insurance products tailored to the unique technical risks of modern autonomous and agentic AI environments. The specific products mentioned include 1. Autonomous systems and robotics. 2. Model, data, and infra security. 3. Coverage for agentic AI systems and conversational agents.
Next, I'll grab one of the products and ask for more information using a text query.
Autonomous system and robotics coverage is a type of insurance product offered by AI Agent Ensure, providing liability coverage for bodily injury or property damage caused by autonomous systems, including autonomous vehicles, drones, robots, and industrial automation units.
Next, let's enter a query which the agent will go against the SQLite database for the response. And we see the agent responded with 100 insureds in the database, which we can confirm. Now I'll send an audio query, which also requires retrieval from the database. How many claims have been filed?
How many claims have been filed?
And we see the agent responded with 46 claims, which we can also confirm. And for our final test, we'll ask the agent to retrieve information for insured with an ID of 1, which isn't in the database, but we do get data back when we use an ID that is in the database, which we can confirm. Now, in addition to implementing the agent, I also built an app to evaluate performance of the agent. However, before I run this, let's jump into the agent's config file and change the retrieval k property value from 4 to 2. This parameter indicates the number of top-ranked, most relevant documents or data chunks that the retrieval system fetches from the knowledge base to provide as context to the LLM. And as we can see in the comment, a higher value typically yields a better retrieval accuracy. Now, with Ollama running, I'll kick off the test script, which will run through a series of sample questions requiring the agent to retrieve data from the vector store and the SQL database. And as we can see here, the success rate was 90%. When the eval app runs, it stores its results as a JSON file, which is loaded into a Jupyter notebook to be used for further evaluation. So here I'll run the imports, load the results file, then display summary statistics on the test results, which confirm our 90% success rate. And here we see that it was one of the RAG tests that failed. Next, we get a plot of the success rate, then details of each test, as well as a list of the tests that failed. In the interest of time, and so we don't repeat the steps we just went through, I pre-ran tests with retrieval k settings of 2, 4, and 6, and created a notebook to compare the results. Here, we see that the 3 test files were loaded and stats on the tests. Looking at the success rate by the retrieval k value, we see that the tests with size 2 outperformed the higher values, which, as you may recall, is opposite of what we would expect when executing with higher retrieval values. Now, previously we ran a test with retrieval k set to 2, and the result was 90% accuracy. So why do we see a variation here? Well, this could be due to a few reasons. First, a RAG system can show variable performance on multiple runs with different retrieval k values, 2, 4, and 6, even with the same vector store we previously ran against, due to the nature of the information retrieved, the model's processing capabilities, and inherent randomness in the retrieval and generation process. Second, while using the same vector store, the specific documents retrieved can vary slightly between queries due to minor numerical precision differences in vector similarity calculations. And third, we may be experiencing a phenomenon known as the lost in the middle effect, where as you increase k from 2 to 4 to 6, you're feeding the LLM a progressively longer context window. When k equals 2, we get a precise, focused context. If the 2 most relevant chunks are retrieved, the LLM is likely to use them effectively and generate a high-quality answer. When k equals 4 or k equals 6, more chunks are added, and even if some of them are relevant, others are likely to include more noise. So the LLM struggles to effectively utilize information embedded in the middle of a large prompt. So now that we've seen a demo of the app and evaluated some of the test results, let's take a look at how RAG processing works. First, in the knowledge base folder, in the directory where this notebook lives, we see a single PDF file which contains information on AI Agent Ensure. Now, let's run the notebook and examine the results. The first thing we'll notice is that the ChromaDB vector store was created, which will be used by the RAG pipeline, which is controlled by LangChain, to retrieve data for the LLM to formulate a response to the user's question. Looking at the steps in the pipeline, we see the process starts with processing the user's query, which is converted into embeddings using the nomic-embed-text model. Then a cosine similarity search is performed to retrieve similar chunks. Then the chunks are combined into context, which the Llama 3.2 model will use in its response. Now let's jump up to the top of the notebook and work our way down the pipeline. Here we've installed the required libraries listed in the requirements text file, and import LangChain and PyPDF. For our configuration, we're specifying Llama 3.2 3 billion for the LLM model and nomic-embed-text for the embedding model. The temperature is 0.1. We'll specify a chunk size of 1800 with a 350 character overlap, and retrieval K is set to 4. We'll start by loading the PDF document using the PDF reader, and then call extract text on the page in pages and setting that as the value for the text variable. Then we'll append the text in the source to the documents list. Next, we'll display the PDF content, which comes from the overview PDF file and is 4010 characters. The next step is to split the document into chunks, for which we'll use the recursive character text splitter, passing the chunk size and overlap declared above and setting the result as an instance of the text splitter. Then for each document in documents, we'll call split text on the document's text and store it in chunks. Then we'll extend all chunks, giving it the current chunks, and then extend the metadata specifying the source of the document. And we see we've created 3 chunks from our one PDF file. Here we can view the chunks, and then we'll create the vector store. So first we check to see if the vector store has already been created. If it has, we'll instantiate an instance of the Ollama embeddings object, which will pass as the value for the embedding functions parameter and store the results of calling chroma in the vector store. In our case, we haven't yet created the vector store, so again we'll instantiate an instance of the Ollama embeddings object, call the fromText method on chroma, passing it the chunks as the value for the text property, the embeddings, the metadata, and where to persist the vector store. And our vector store has been created, which contains 3 document chunks. Now we'll set up the RAG chain. Here we'll call chat Ollama, passing it the LLM model, the temperature, and a timeout, and set the result to the value of the LLM variable. We'll set up conversational summary memory, giving it the LLM, chat history as the memory key, and pass other parameters, and store the result in memory. Here we'll declare the custom template, which we'll inject the context and the user question into, and then pass the template to the prompt template function to instantiate an instance of the prompt template, specifying the input variables of context, chat history, and question, and store the result in the QA prompt constant. We'll set up a retriever, calling the asRetriever method on the vector store, and indicate that the search type will be similarity, and setting k equal to the value of the retrieval k of 4, which we set above. Then we'll call the fromLLM method on the conversational retrieval chain and set the result into our question and answer chain. Now with the RAG chain ready, we could declare a question, pass it into the QA chain, and set answer equal to the answer property on the result, which is the question and answer chain. Then we'll populate sources and review the chunks. So here we see 3 chunks were retrieved based on the semantic similarity search to the question passed in, all of which came from the overview. And finally, we'll print the answer to the user's query. Now we'll try another question. What products does this company offer? Pass the question to the QA chain, get the answer as we did before, and then display the answer, which we see here. So that concludes the demo of my final project. I hope you found it interesting.